So Zener is just another diode. The only difference is that it actually operates in the reverse breakdown as well as forward biasing. So when it's in forward biasing, it's going to act like a normal diode, and it's going to drop its 0.7. When it's in the reverse biasing, then it's going to have what we call a Zener voltage, and that can be set up to be any voltage anywhere from 1.8 volts up to 300 volts. No, you don't got this yet. Yep, yeah, that one. Yeah, I got it. Now, I'll leave this on your, I did hand it out. That, if you did grab that on Friday, then you need those. I just left these on the printer the other day.
Staple. Nice. Geez, Kurt, you're cutting back on the paper.
No. To make up for it in transistors. So here's what the symbol for the Zener diode looks like. So just like the regular diode, it's going to have its anode, the white part of the arrow, and then the cathode. And then another name for a Zener diode is also considered an avalanche diode. And typically they start calling the avalanche diodes after the reverse biasing of the Zener is greater than 5 volts. Otherwise, they're all categorized as pretty much a Zener diode and stuff like that. But if the reverse biasing of the Zener is greater than 5 volts, then we call them the avalanche diodes. So again, when for the ideal diode and for our approximations and stuff, if we're more positive on our anode and more negative on our cathode, then it's going to drop our 0.7 volts, just like the regular diode. If we put the Zener into a reverse biasing, and we're more negative on our anode and more positive on our cathode, what we have to do is we have to break down, we have to make sure that we're greater than whatever our rated Zener voltage is. And again, it can be anywhere all the way up to 300 volts. So if we're more negative on our anode and more positive on our anode, and this Zener, for example, is the voltage of this Zener is 5.1 volts, then we have to be more negative on our anode than our cathode by 5.1 volts. And once we achieve that, then once we get to be more negative on our anode by the Zener voltage, then that Zener is going to drop whatever the Zener voltage is. So on this one here, since the Zener voltage on this rated Zener here once we get more negative on that anode, then the voltage across the Zener is going to drop down to 5.1 volts. Just like the regular, when it's in the regular diode mode, no matter what I do to my power supply, if I just keep on increasing my source voltage to it, the Zener is going to always just drop whatever the Zener voltage is. So for example, on this one here would be the 5.1 volts. It would never go greater than that. And so what we can do is that we use these Zeners a lot of times for either regulating small current power supplies, or use them for reference voltages going into other circuits like op amps and stuff like that. Because they're so consistent, you know, and no matter what happens to my voltage going into it, as long as I have that voltage potential greater than the 5.1 volts, it's going to maintain that 5.1 volts. And so they're ideal circuits, ideal components for setting up ourselves for reference voltages and stuff like that. So again, just like a regular diode, these are current-driven components, and they'll take as much current as you give them if you don't have that current limiting resistor in there. So you always have to have that when we're working with solid-state devices. We always have to have our current limiting resistors in there to maintain the current going through that diode. Otherwise, it's going to take all the current it wants until it exceeds its power rating, and it'll end up burning up. So that's so let's take a look at just analyzing some of these circuits here for our Zeners. So let's just like we did with the other regular diodes, what's our first thing that we want to do before we
circle your active components?
Yeah, circle your active component. So our active component is here, and again, we still have our anode here, and then our cathode where the line is. Then what's my next step?
Treat it as an open.
Yeah, treat it as an open. So we're going to treat it as an open, and then what's our next step?
Find the soft voltage.
Yeah, find your soft voltages. And it's just basically just like if you're going to be putting your voltmeter on your reference, bringing your red lead up above it, treating that diode as an open. What would I measure for voltage above this on the anode side?
10 volts.
Yeah, and don't forget your polarities, and it's going to be a positive 10 volts. And then on my cathode side, what would I have for a soft voltage?
Plus or minus 0.
Plus or minus 0. Okay, then now we have to now we look at our voltage on our anode, and we look at our voltage on our cathode. Is my anode voltage more positive than my cathode?
Yes.
Yeah. So then we have to ask ourselves then, is this either going to be a go diode, go Zener, or no go? So would this be a yeah, it's going to be a go. It's going to be a go diode because we're more positive on our anode, more negative on our cathodes. It's going to put that into a diode operation. So if it's in a diode operation, so it's going to be a go. It's going to be in a diode operation. What's it going to drop for a voltage then?
0.7 volts.
0.7 volts. Okay, then what's my next step?
Figure out your VR.
Yeah, so figure out my VR, because we already gave the diode its voltage. We only have two components on here, so VR is going to equal to what?
9.3.
It's going to equal our 9.3 volts. Then what's my next step?
Figure out your currents.
Yeah, so then we got enough information, we can go ahead and jump down towards the bottom there. We can figure out our current. So what's my current going to equal to?
9.3.
Yeah, so it's going to be 9.3 milliamps across my resistor, and it's going to be across the diode. So then my diode is going to have also 9.3 milliamps going through the diode since it's a series circuit. All right, then let's just jump back up. Now, what's my voltage going to be at test point A?
Plus 0.7 volts.
Plus 0.7 volts. Bring your red lead down to your black lead. And then what's going to be the power of my diode then?
86.49 milliwatts.
6.49?
Oh, wait a minute. Nope. 60.54 milliwatts.
What is it, 6.54?
60.54.
60.54. Is that what everyone else got?
No.
No, that's not what I got either.
I had 6.51.
Yeah, I don't know how you times it by 10, but it should have been somewhere around 6.51, 6.54. Maybe what you used. Should have got 6.51
I got
milliwatts.
52.68 milliwatts.
All right, so to calculate all power, what's
I times E.
I times E, right?
9.3.
So you should be taking your 0.7 volts times your 9.3 milliamps. That equals your power. So what's 9.3 times 0.7?
6.510.
Yeah, so I got 6.51.
I got that too.
Yeah. Chapter 3. All right, so that's what you should have gotten at 6.51 milliwatts then. All right, so that's just like a regular diode then. All right, so now circuit number 2 here. Okay, our first step is to do what?
Circle the active component.
Circle the active component. Put in our polarities. Okay, then my next step.
Find the soft voltage.
Yeah, find the soft voltage. So we're going to treat that diode as an open. My soft voltage on my cathode side is going to be what? Yeah, plus 10 volts. Don't forget the polarities. And then on my anode side is going to be what?
Plus or minus 0.
Plus or minus 0.
Is this where it's going to be like shove there and here and there?
Yeah, so here's our Zener operation and our diode operation. Yeah, so we already identified that if we have enough voltage potential across from our cathode to our anode, we know that we're going to be in a Zener operation, but we have to make sure that since we're in a Zener operation, that make sure that our voltage potential is greater than 5.1 volts. So are we greater than 5.1 volts per voltage potential across that?
Yes.
Yes. And so we know that it's going to become a Zener. Then it's going to drop its voltage first, and what's the Zener going to drop for voltage?
5.1 volts.
5.1 volts. Okay, so no matter if it's a diode or a Zener, it's always going to drop its voltage first. So the Zener dropped 5.1 volts. How much is left across the resistor then?
4.9.
4.9 volts. And then we'll go right down the row this time. So then what's my voltage at test point A going to be?
Plus
5.1.
Plus 0.51.
5.1.
5.1. Plus 5.1 volts. It's going to be at test point A then. Voltage across the Zener. And then what's the current going through the diode?
4.9 milliamps.
4.9 milliamps, because that's the current going through the resistor. And if that's the current going through the resistor, then we know that has to be the current going through the diode, 4.9 milliamps. And what is going to be the power of my diode?
24.99 milliwatts.
24.99 milliwatts. 5 times E. Alright. Pretty straightforward. Should be. Alright. Circuit number 3 then. So we're going to circle our active component, put in our polarities inside there, bring down our soft voltages, and what am I going to have for a soft voltage on my anode side?
Minus 15 volts.
Yeah, minus 15 volts. And then on my cathode side, I'm going to have what for voltage?
Plus or minus 0.
Plus or minus 0. Then determine whether it's go diode, go Zener, or no go.
Go Zener.
Go Zener. And then the voltage across the Zener is going to be what?
12.1 volts.
12.1 volts. Okay, and then the voltage across the resistor is going to be what?
2.9 volts.
2.9 volts, the remainder amount of voltage. If we had more than one resistor in there, you would just divide up that 2.9 volts across the other 2 resistors. So in this case, we only have the one. Then we calculate out the current going through the diode by whatever the current is going through R1. So what's my current going through R1?
2.9 milliamps.
2.9 milliamps. That's our current going through our diode, or through our resistors, and that's the current going through our diode. And my power is going to equal to what?
35.09 milliwatts.
35.09
Yep.
milliwatts. Oh, what's our voltage at test point A?
Minus 12.1. Is it minus?
Yep, negative 12.1.
Negative 12.
Yeah, negative 12.1 volts. Yeah, it's because we're more negative on our anode than we are on our cathode, so we know that the current going through the diode, we should always kind of draw our current going through our diode, so we know our current is going north or going south. Polarity across there. Yeah. All right. And circuit number 4. Circle our active component, put the polarities inside. Determine our soft voltage. So our soft voltage on our cathode is going to be what? Plus 12 volts. And on our anode side?
Plus 0.
Yeah,
Plus or minus.
plus or minus 0 volts.
No.
Determine if it's
It's a no-go.
well, determine either if it's a go Zener, go diode, or a no-go. So we're more positive on our cathode than we are on our anode.
Zener.
Yeah.
Yeah, it's a go Zener because we're more positive on our cathode than we are on our anode. And we have a voltage potential difference between greater than 9.1 volts. So I had to go another go Zener. And it's going to drop what for voltage?
9.1.
9.1 volts. Zener voltage. Okay, then our voltage across R1 then? 2.9. 2.9 volts. Current going through our Zener.
2.9 milliamps.
Yep, 2.9 milliamps. Whatever the current is that we calculate out through the resistor, it's going to be the current going through the diode. And my power is going to be what? What was it?
26.39 kilowatts.
26.39 kilowatts.
Then current's 0.8
Oh yeah, and test point A is going to be what?
plus 9.1 volts.
Yeah. Because we are more positive on our cathode, so our polarity is, and our current is going this way. And so we're going to be plus 9.1 volts. But no matter what I do to this voltage supply, as long as I maintain a voltage potential greater than 9.1 volts, my test point A is always going to maintain 9.1 volts no matter what happens to my source voltage, as long as my source voltage doesn't drop below 9.1 volts. So I always will maintain that positive 9.1 volts at test point A. Alright, let's move up the last one here. Okay, and then the last one, circle the active component. Put our polarities inside there, bring down our soft voltages. So on my anode side, I'm going to have what for soft voltage?
Negative 10 volts.
Negative 10 volts. And then on my cathode side, I'm going to have what?
Plus or minus 0.
Plus or minus 0. So I'm more negative on my anode side than I am on my cathode side. Yep, then I'm greater than my Zener voltage of 2.4 volts. So I know that's going to be a go Zener. And it's going to drop its voltage of 2.4 volts.
On the test something you want us to write goes here on there? Not just.
Yep. Yep. Yeah, don't just write a go, because then I would assume that you're talking about go diode. Yeah.
I was making sure.
Yep. Good question. Yeah. Yeah. So write down there. Identify whether it's a go Zener, go diode, or no go. All right. So then my voltage across my resistor is going to be what?
7.6 volts.
7.6 volts. And it's going to have what for current?
7.6 milliamps.
7.6 milliamps. And my voltage at test point A?
2.4 negative.
Yes, negative 2.4 volts. Oh, and then my power for my diode?
18.24 milliwatts.
What was it?
18.24 milliwatts.
18.24 kilowatts. Alright. So pretty straightforward. Alright. If you want, I do have other lectures and stuff like that, but I think you get the understanding of how Zener works. But if you do want some more practice, I do have a couple more lectures that little different configurations and stuff like that, but how we understand how a Zener works. I want to get more into the application of treating it as a regulator. And also on how to how to design a circuit. Kind of like what we talked about in Tech Doc, you know, kind of going backwards. Nope, that's your lab.
Yeah, we got this.
This is lecture.
Oh, I didn't know that.
Yeah, this is lecture 1.
Don't we already have one of these?
That's your lab.
Oh. Oh, that makes sense.
There's a short one there.
Okay.
Then we're going to start using data sheets, especially when we get into transistors. All right, so here's a basic Zener regulator circuit. So we're gonna so for a basic Zener regulated circuit, then it's going to consist of RS, which is our current limiting resistor, our Zener, and then whatever our load is. The Zener is going to have a certain amount of voltage. You know, you can specify whatever voltage you want in there. So, for example, on this one here, if we're going to have a Zener voltage of 12 volts. Then our load, is that in series or in parallel with our Zener? It's in parallel. So whatever remains constant in a parallel circuit? Voltage. So whatever our voltage of our Zener is going to be whatever our voltage of our load is. So there's how we're going to maintain our voltage regulation by having our load put across our Zener voltage. So the Zener is still going to always take its voltage first. It's going to drop its voltage first. It's going to drop its 12 volts. And then the voltage across the load is going to be 12 volts. Now this is where it gets kind of be a little tricky here, because there's certain things that we have to watch out for. And since diodes are current-driven devices, we need to maintain not just the voltage potential across there, but also we have to maintain a certain amount of voltage going across that Zener. If we don't maintain a certain enough current going through that Zener, then what we call it is it's going to drop out of regulations. So if we're looking on so if we look on page 752 is our diode characteristics curves. So on our regular diode and on our curve tracer, on a regular diode, when it was in the reverse biasing, our negative voltage here, our positive voltage here, positive current there, and our positive current here, or negative current here. When it was in the reverse biasing of that diode, there was no current. It acted like a closed switch. And it just kind of maintained it. Then it hit that 0.7, and then all of a sudden the current shot up. Okay? So once we hit that 0.7 volts, the diode turned on, and the current started to flow through it. Now with the Zener, we actually look at, well, then all of a sudden we start applying enough reverse voltage across it. So for example, on here is our 12 volts, or negative 12 volts, reverse biasing. What happens is once it hits that 12 volts, then that diode is going to turn on. And then that current is going to start to, I'm going to exaggerate that a little bit more. So at about approximately 12 volts, that Zener is going to turn on. But we kind of have this little area here where as we start to go, here's 0 volts, and I start to increase. I'm getting a little bit closer to my 12 volts, but I'm not at my 12 volts. I'm just getting a little, but that diode or that Zener is already starting to turn on, and the current is starting to flow through there. And then once I hit that 12 volts, then my line here starts to go more straight up and down. Here's kind of more of an arch and stuff, and the current is slowly increasing as the voltage still is increasing across the Zener. Then once it hits that approximately about 12 volts, then it's going to maintain that 12 volts, and then the only thing that really increases is just my current. And so what we like, so we don't like to be in this area here. Where we want to be is we want to be somewhere at this area. So we want to maintain our certain amount of current going through there at our 12 volts. And this little spot here is what we call our IZK. This is our knee current. It's kind of like, somebody sitting on a chair and they're bending their knee. The knee current is what we're trying to look for. We need to maintain that certain amount of current to maintain regulation. So we need to maintain that knee current. And then if you're looking on your data sheet there, and you look at what your IZK is, it's underneath the category of the maximum Zener impedance. And if you look all the way down, if you go down to the 1N4742A, that's a 12 volt Zener. The test current is at 21 milliamps. That's where they ended up getting that actual. This is going to be the actual voltage that they measure, the Zener voltage at our test current. So they're going to make sure that they have 21 milliamps of current. They're going to read what that voltage is of the Zener is. And then if you keep on scrolling over to the right there, then it says the IZK, 0.25 milliamps or 250 microamps. That is this knee current right here. That's our minimum amount of current that we have to have on this Zener and still have it maintain the regulation of it. Okay? So they get the test voltage from our test current. They're going to run it up to 21 milliamps, that's our test current, and they measure the Zener voltage, and that's where we get the voltage. Then maintain that regulation. They spec'd it out saying that to maintain regulation, we have to have that neat current of 250 microamps or 0.25 milliamps.
I gotta make sure I got the right sheet here.
So for the 12 volt Zener that we're going to use the 1N 4742, and then we'll refer to the data sheet that's listed underneath there. So the nominal Zener voltage we already identified is going to be our 12 volts. So I'm just doing this right, getting this right off your lecture sheet right below here. My test current for that nominal voltage, they did the test current at what at how many amps?
21 milliamps.
21 milliamps. My neat current to maintain regulation is going to be how much per amps? 250 microamps. And then what's my power of this diode? What's the maximum power that I can have going across this diode? So look on your data sheet and find out what the maximum power is across this diode that I can have. Don't look too far down.
Is it 1?
Yeah, 1 watt. Right up towards the top. So no matter what my Zener voltage is, any one of those in that family of Zeners is going to be 1 watt. So that's going to be my maximum power that I can have across this diode without damaging it. So my power dissipation is 1 watt across. All right. So now we're going to go down to step 2 and start looking at okay, so step 2 then is it's going to be my IT max. So what would be the maximum amount of current that I can have going through that Zener without damaging it? Current. How much current can I have going through that? How much current can I have going through that Zener without damaging it? How would I determine it?
Take your maximum voltage and something.
Huh?
Take your max voltage divided by your resistance of ZK.
Something a little simpler than that. I'll give you kind of a hint. I was kind of asking about the power before.
Yep, power divided by voltage.
There you go. Yep. So we know that power is equal to IE. You remember, if we always know 2 things, then we can always find the third. So we know that the power is going to be equal to 1 watt. And my voltage across my Zener is going to be 12 volts. So then that will just leave us I. So if I just take my 1 watt divided by my 12 volts, that'll give me my current max going through my Zener. So what can I have for a maximum amount of current going through that Zener?
83.33 milliamps.
Wouldn't you use the
Why don't
maximum
you use your maximum value?
of 12.6 off of the rating on the sheet?
No. Typically, we always look at the nominal ratings. They're just saying that they could have. So if I were to buy those Zeners, and when they're manufacturing, they're just going to guarantee it that it's going to be within 11.4 volts all the way up to 12.6 volts.
Okay.
But when we always do our approximations, we always use with that nominal voltage. What is the typical voltage of any of that given Zener? But that's just kind of their specs, just saying that they can maintain that voltage across any one of those given Zeners that comes off the product line. That's going to be within 11.4 to 12.6 volts. But when we always do our approximations, we use our nominal, our typical voltage there. That's a good question though, but yeah. Now there might be a case where you might need to, if you're really on the borderline of, on your circuits, you might want to use that number for some other particular application though. So not necessarily is that we've never used it, but typically we use the nominal one. But yeah, there might be times where you would use that, put the maximum voltages or the minimum voltages. Yep, so, and again, it doesn't matter which diode in that family. All I'm going to do is figure out what that maximum current is going through that diode that can allow to maintain that wattage. It's just going to be taking what's the rated wattage of that diode, and divided by whatever that Zener voltage is. And that's going to be my current max for any given one of those particular Zeners. So for example, let's say if I had a 5.1 Zener, would I be able to have more or less current going through that Zener if it was only a 5.1 volt Zener? More. Yeah. Because my voltage and my current, are they directly proportional or inversely proportional? Inversely. So if my Zener voltage goes down, my current then is going to go up. So on the smaller voltages, I can maintain more of a maximum current going through that diode. All right. I look on two different sheets here. All right, so now we're going to go ahead and we'll analyze our circuit here. So we know that we're going to have our 12 volt Zener in here. So our first thing is that we want to know is what is going to be our minimum current there of our load. Let's see, I got one. Yeah, I'm gonna change your. So on your sheet there, we're under the load output. Load output regulation. We're going to change that to 100 ohms. So RS is going to be 100 ohms. here, but I gotta match mine up here. Damn good. Because mine goes from, I started out at 12 volts and then I mine got changed here, so I want to make sure everything will work okay. So what we're going to take a look at is we're going to start completing our second table here. I do want to make sure. What I'm going to do.
Are you talking about this table right here?
Yeah. My tables, for some reason, I got the wrong table on my answer key. Let's take a quick 10-minute one. I want to make sure I got the right answer key.
Yeah,
What's that?